way across. 4, 3, 2, we have main engine start, 0, and liftoff of the Stardust spacecraft, returning a time capsule with the elements of the formation of our solar system.
Since the launch of Stardust in 1999, there have been 6 attempts to journey into interplanetary space and return to Earth with an extraterrestrial sample. As of December 2020, 4 of these samples have successfully returned to Earth, and OSIRIS-REx is on its way home. Today, we're designing a trajectory for the next major step in interplanetary sample return, in Interplanet's Odyssey, Destination Ceres. The mission concept is simple on the surface. A spacecraft must be launched from Earth between 2035 and 2045. From there, it has 12 years to journey to Ceres, enter a polar reconnaissance orbit, collect a sample, and then return safely to Earth. A few key metrics also drive the design. Specifically, the total delta-V required after interplanetary injection, total time of flight, spacecraft mass, C3 energy required at departure, and whether any flybys are conducted to enhance the trajectory. As the largest object in the asteroid belt, Ceres was last visited by the Dawn spacecraft, which concluded its 3-year exploration of Ceres in 2018. While it is not currently under consideration for a NASA mission, Ceres has shown potential to be an ocean world, like Enceladus or Titan, 2 moons of Saturn who are key candidates for NASA's New Frontiers 5 mission. Analysis of the Ceres Odyssey begins with the constraints. The mission must take no more than 12 years, the spacecraft may not travel closer than 0.6 AU to the Sun, a dry mass of 1,200 kilograms with a 300 kilogram lander totals a minimum 1,500 kilogram mass for the craft, and the trajectory must be accomplished with currently available technology. In order to find this trajectory, a software-driven workflow was used. First, ephemeris data was collected from the JPL Horizons database. MATLAB and Python polyastro libraries were then used to build workshop plots with Lambert's problem. These plots would provide a baseline for departure and arrival windows that would then be analyzed in JPL's Malto software to generate and optimize trajectories. A Tisserand plot would also be used to analyze potential gravity assist tours that would reduce delta-V or enhance mass delivered to Ceres with a lower departure V infinity. Finally, an optimized Malto trajectory would be brought into FreeFlyer or NASA's GMAT software for visualization and further analysis. Various assumptions were made to simplify the analytical process, primarily that all influences except for gravity were neglected, with the body's gravity modeled as a perfectly spherical point mass to accelerate computation. Additionally, spacecraft hardware such as fuel tanks would sustain no mass loss from boil-off or leaks during the flight. Solar panels would only lose efficiency due to distance from the sun, and not time in operation. There would also be no issues relighting the engines at any time in deep space. 3 options for trajectories were considered. First, a fully impulsive trajectory provided by NASA Ames' trajectory browser. Second, a fully low-thrust trajectory that was modeled entirely in Malto. And finally, a hybrid trajectory that uses both low-thrust and impulsive maneuvers. After consideration of each trajectory option, the hybrid was selected. While the impulsive trajectory was significantly faster than the ones containing low thrust, the cost was an infeasibly high amount of propellant mass to complete the capture of Ceres. The low thrust trajectory, on the other hand, was very feasible, but due to time of flight constraints, the hybrid was selected over it to save time during Ceres capture and during maneuvers around Ceres. With this in mind, let us now walk through the final selected design. An Earth-Venus-Earth-Mars Ceres Grand Tour. Our mothership is the Rocinante. She is equipped with SpaceX Super Draco thrusters for impulsive maneuvers and the next GRC 6500 ISP ion engine for its low thrust maneuvers. Also included is a high-gain antenna for communication with the Deep Space Network, a remote sensing package for reconnaissance of Ceres. And its solar arrays produce an impressive peak power of 50 kilowatts at launch to ensure plenty of margin for ion operations. Shortly before Christmas Day in 2035, the Rocinante will be loaded on top of a SpaceX Falcon Heavy for its grand odyssey of the inner planets. With a very low departure C3 of only 27.59, there is significant mass margin for the 3,000 kg Rocinante at launch. Our Falcon Heavy will fly in a reusable configuration, but with the same trajectory, an expendable Falcon Heavy could deliver almost triple the mass. After a short parking period to check out spacecraft systems, the Merlin upper stage will catapult the Rocinante into an Earth escape trajectory, where the craft will journey towards its first destination. 225 days into the journey, the Rocinante arrives at Venus. Flying by at an altitude of 1,000 kilometers, the spacecraft has the option to deposit or retrieve additional spacecraft if desired. For this trajectory, a simulated 200 kilograms of smallsat was dropped off to explore Venus's atmosphere for signs of life. On day 540 of our Ceres Odyssey, the Rocinante returns to Earth for a daring flyby at only 300 kilometers of altitude to catapult to Ceres with 3 kilometers per second more V-infinity than it was launched with. Here, we exchange no mass, but the architecture could allow for the return of a Venus sample received on our previous leg. After coasting away from Earth, on day 733, the Rocinante fires up its low thrust engine again, but this time it is to conduct a powered flyby of Mars. Similar to the Venus flyby, 100 kilograms of small sats will be dropped off as our ship passes within 200 kilometers of the Martian surface. The Mars-powered flyby changes our heliocentric energy and deflects the resulting trajectory into the plane of Ceres, reducing the delta V required to capture. Now on the correct orbital plane, the Rocinante will coast in interplanetary space for just under 2,000 days until it arrives at Ceres. Along the way, there will be 2 low-thrust trajectory correction burns to match Ceres' orbit. One final 124 meter per second maneuver with the Super Draco thrusters captures the Rocinante into the orbit of Ceres. Just over 7 years after launch, our ship has finally arrived, having used only 5.5 kilometers per second of delta V and about 222 kilograms of fuel. Upon arrival at Ceres, the spacecraft will insert into an 800-kilometer radius polar reconnaissance orbit to map out a precise landing site. Once the site is selected, the lander, Convector, will detach from the mothership and descend to the surface of Ceres. Two samples will be collected, one from Ocator, a large crater thought to contain the highest concentration of carbonate materials outside of Earth, and large salt deposits that appear brightly in reconnaissance imagery. Ahuna Mons is a second landing site, likely formed by cryovolcanic activity that is a combination of mud and saline water. The lander will hop on a parabolic trajectory between the two sites to collect 10 kilograms from each. Following initial landing on the surface of Ceres, the lander will have approximately 1.5 years to collect samples and conduct surface experiments. Once the mission has concluded at Ahuna Mons, the lander will have an opportunity once every 13 days to launch and rendezvous with the mothership with minimal delta V. It is calculated that approximately 310 kilograms of propellant mass will be required for the lander to complete its dual sample return mission. Once rendezvous is complete, no hardware will be left in Ceres orbit or on the surface to meet the highest standard of planetary protection. No earlier than January 16, 2045, the Rocinante will begin spiraling out with its low-thrust engine. 30 days later, our ship leaves Ceres' sphere of influence and embarks on its journey home. From departure, 10.87 kilometers per second of delta V are burnt in a constant low-thrust maneuver all the way back to Earth. By the time the spacecraft arrives at Earth's sphere of influence, its V-infinity has been reduced to 6 kilometers per second for the return capsule's safe re-entry. A hard-burning return trajectory was selected to return to Earth as fast as possible. Arriving on October 16, 2047, our mission concludes just a hair under the 12-year mark. 240 kilograms of propellant mass remain on the spacecraft. It is possible that future analysis into an extended mission could allow the Rocinante to continue onwards, to continue its exploration of our solar system for years to come.